second period. So today we're going to talk about asymptotes. And we've actually already done part of this, but so there's two things I'm going to talk about: vertical and horizontal asymptotes. I've kind of already talked about vertical asymptotes, but I want to talk about some of the trickier problems, and then I need to talk about horizontal asymptotes. So let's consider. So if I start with what's the limit as x approaches 3 from the right, 2x over x minus 3, and what's the limit as x approaches 3 from the left of 2x over x minus 3. So I want to figure out what these are. Now, as far as computing, what's our limit as x approaches 3 from the right? Well, if we look at this function, we automatically know we've got a vertical asymptote. How do we know that? Well, anytime you're dividing by 0, where it's something, whatever makes the bottom 0, as long as you don't have 0 on top, is going to be a vertical asymptote. So in my mind, not that you actually have to graph this, but in my mind, what I see is at 3, I've got a vertical asymptote. And what this is asking is, where are we going? Are we going all the way up? Or are we going all the way down? And how do you do that? Well, what you do is, if I want to know what's the limit as x approaches 3 from the right, you think you've got to figure out what's happening to the right of 3. So you need to, what I always teach is plug in a value that's just to the right of 3. And don't just pick 4. Pick something really close to 3. So in this case, I'm going to pick 3.1. So if I start out, here's my lovely XY chart. I want to plug in 3.1. Now, before you think this is going to make your life miserable because the numbers are ugly, I don't care what the actual, you're not going to care what the actual number is. All you care about is if it's positive or negative. Let me explain. As you get close to a vertical asymptote, you have two options. You're either going all the way up or you're going all the way down. You're never going to go to the middle and stop. And so if I plug in 3.1 and I get a positive number, then if it's positive, if I'm on this side and it's positive, that's telling me I'm going all the way up. Similarly, if I get a negative number, that means I'm going all the way down. So I don't really need to know exactly what the number is. All I really need to know is this thing going to be positive or negative? And that's actually pretty easy that's usually very easy to identify. So if I plug in 3.1, let's see. I'm going to plug in 3.1 at the top. Well, 2 times 3.1, I don't really care, but I know it's positive. I'm going to plug in 3.1 at the bottom. 3.1 minus 3, I know that's also positive. And I have positive over positive. Well, that's going to be a positive number. And because when I plug in something just to the right and I get a positive number, that's telling me, oh, this thing's it's positive, it's going all the way up. So I can say that this is going to positive infinity. In a similar manner, if I want to figure out what's happening as x approaches 3 from the left, I'll think, well, what's something really close to 3 but on the left-hand side? Well, I'm going to plug in 2.9. And again, I don't care what the actual number is. I just care if I'm getting something positive or negative. So when I plug in 2.9 at the top, 2 times whatever that is, well, I know that's positive. When I do 2.9 minus 3, I know that's negative. Positive over negative is negative. And since I'm going to get a negative number, even though I don't know exactly what it is, I don't care. I just know it's negative, meaning this thing's going all the way down, so I know that this is going to go to negative infinity. So that part kind of makes sense, right? It's important that whenever you see particularly a rational function, that you can easily identify when you have vertical asymptotes. It's also important that you can easily identify, are you going all the way up or all the way down, without figuring out the exact ugly number. You just care, is it positive or is it negative? And I've already talked a little bit about this, but I need to talk about uglier versions. These are pretty tame. Like you had to do something like, I bet you had to do stuff like this last year. Now I need to talk about what happens when they're not very nice. What if I ask, what's the limit as x approaches 3 of 2x over 1 minus cosine of x minus 3. And this officially qualifies as ugly because it's got a trig function in it. Oh, wait, I'm going to say I'm going from the right. Right? Well, first we have to establish what exactly is going on. Anytime you see a fraction, anytime the bottom is 0, chances are we've got a vertical asymptote. So let's see what's happening at 3. If I plug 3 in, well, 3 minus 3 is 0. Cosine of 0 is 1. 1 minus 1 is 0. This, at 3, I've got a vertical asymptote. So if I'm graphing it, I'm going to have, I got a vertical asymptote. I got to figure out what's happening on either side. So, what's happening to the right? Well, so we've got some good news and bad news. The bad news is, it's a trig function, and most people hate trig functions because they forgot everything from last year. The good news is, sometimes trig functions make your life a little bit easier. And here's why. So for this particular problem, I look at this and I see cosine. And I remember that cosine doesn't have a whole lot of values. It doesn't cover everything. I mean, officially we're talking about the range of cosine, but I try not to use math terms if I can. When I deal with cosine, I think, well, the biggest cosine gets is 1, and the smallest cosine gets is -1. Because, this was your picture of this was your graph of cosine. It started here and it did this, and it's a nice big wave. The biggest it got was 1, the smallest it got was -1. Well, let's think about what happens to the bottom. If I think about what happens to the bottom, the only way this thing ever equals 0 is when this equals 1. And that's the biggest cosine ever gets. Most of the time, cosine is less than 1. And since most of the time cosine is less than 1, if I just move a little bit off 3, this is going to be less than 1, and 1 minus something smaller than that's definitely going to be positive. But here, let's kind of treat this the same way I did the previous problem. If I'm interested in 3 from the right, okay, well, I have my little XY chart. I care about what's happening at like 3.1. Well, 3.1 on the top, let's see, 2 times that's still positive. But 3.1 on the bottom, well, this is 1 minus cosine of 3.1 minus 3 of 0.1. What you're going to find out is this is going to be a number less than 1. I don't know exactly what it is, and to be honest, I really don't care. All I know is it's not 1, which would have been up here, so it's going to be a little bit less than 1. So 1 minus something smaller than 1 is definitely going to be positive. So I get positive over positive, and that gives me positive. All right? What happens if I do the limit as x approaches 3 from the left of this ugly thing? 1 minus cosine of x minus 3. Well, now I'm going to plug in 2.9 and kind of do the same thing. I plug in 2.9, 2 times 2.9, well, that's positive. And when I plug this in, I get 1 minus, ends up being cosine of -0.1, which, again, seems intimidating. But if you think about what the graph of cosine is, the biggest this thing ever gets is 1. And if I move anything off 0, it's going to be less than 1. So this is going to be 1 minus something smaller than 1. And so that it's going to also give me a positive number. So I get positive over positive, which is positive. So cosine of the trig functions, cosine's actually, I think, the easiest to work with because pretty much it's going to generate some sort of positive number. And it's particularly if you pick something just to the left or the right where your asymptote's going to be, it's going to give you something a little bit smaller than 1. I started with this one because there's not a lot of variety with cosine. Sine, on the other hand, is a little different.
So then is cosine always positive?
For the examples that you have, it's not technically it's not always positive because like if I do like cosine of pi, that's -1. That's right. But the way they use cosine in the problems is the denominator, they send the center where you're computing cosine is around 0, and cosine around 0 is 1. And then you'll see some of the examples, and pretty much you get to say, all right, cosine's just going to be a smaller positive number. It ends up being a lot nicer. Sine isn't, because sine, let's say I change the problem and I say this is 2x over sine of x minus 3. And this is going to be 2x over sine of x minus 3. All right? Now, with sine, we have to do a little thinking. We have to remember what's happening with sine. And our graph of sine looks like this. If you remember, it kind of did this thing. And what's important is that if sine is a little bit positive, we get a positive answer. And if it's sine of a little bit negative number, we get something that's a little bit negative. Right? So now when I plug stuff in, let's say sine of 0 is 0, so when we get, as we're approaching from the right, when I plug 3 in, I get a vertical asymptote. So I care about what's happening if I go 3 from the right. Well, let's see, if I go 3 from the right, I'll plug in 3.1. Well, 3.1 times 2, that's positive, so I'm okay with that. When I plug 3.1 into this, that means what's sine of 0.1? Well, if we go back to this picture, sine of a little bit positive is a positive number. So my bottom's positive, so the top's positive, the bottom's positive. At 3.1, it's positive, so this is going to go to positive infinity. On the other side, if I do 2.9 on the bottom, well, 2 times 2.9 is positive, and then this is going to be sine of negative 0.1. Sine of negative 0.1, well, now we're just to the left of the origin. That's going to be a negative value. So I have positive over negative, so this whole thing's going to equal negative infinity. And so that gets a little tricky. Now, so when you have sine, this can happen. But what if I change it? What if instead of asking this, I ask, what's the limit as x approaches 3 of 2x over sine squared x minus 3? Now, officially, I hate this notation. I think all it does is confuse people. It confuses you a little bit in pre-cal. It really confuses people in calculus. And so I just want to remind you, do a refresher, that this means, oh wait, I want to say from the right. This means, what's the limit as x approaches 3 from the right of 2x over sine of x minus 3 squared. Right, this little squared means, say, I'm taking the whole thing squared. Well, how does that change your answer? The answer is not much. Because if I plug in 3.1, the top's still positive, so I'm happy about that. The bottom, I don't have to think very much, do I? Because, can you see that the bottom's guaranteed to be positive? Because no matter whatever's stuck in here, if it's not 0, you squared it. And when you square it, you're guaranteed that the bottom's positive. So anytime I see a fraction where the bottom's squared, I can just go ahead and say, well, I know the bottom's always positive. And so now I have the top's positive and the bottom's positive, so I know that that's going to positive infinity. And if I were to change the question and say, what's the limit as x approaches 3 from the left of 2x over sine of x minus 3 squared. When I plug in like the 2.9, I'm guaranteed that, the top's positive, but I'm also guaranteed the bottom's positive because they've squared it. So I know this is also going to positive infinity. So you've got when you have your trig functions, you like when you see things being squared because you go, well, if it's squared, at least I know it's positive. You'll get the 0 for the vertical asymptote, but if you move just to the left or the right of it, as long as the thing is squared, it's guaranteed positive. And I'm not assigning anything out of the book on this. I'm assigning stuff in Khan Academy. The Khan Academy assignments, they have several questions where they've taken a trig function and squared it. You go, oh, no problem. I just know the bottom's positive. The other thing they have, particularly in the Khan Academy, is they talk about natural log, and it's not fair. They took logarithms out of the pre-calc curriculum, and they stuck it in the accelerated geometry, which means when you took accelerated geometry, you had to rush through it at the end of the year, and there's just not enough time. And then you didn't get to review it last year. So I want to refresh your memory on a couple of key facts with logarithms. One key fact with logarithms are natural log of 1 is 0. All right, that's huge. You need to remember, and this is a fact that we're just going to have to keep using throughout the year. So natural log of 1 is 0. And if they say natural log of like squared x, this is sort of a continuation of that ugly notation I don't like. This means natural log of x quantity squared, which means this is always guaranteed positive unless something happens to be 0. So they did give you some stuff with logs, and I'm just telling, and I think most of the log questions they gave you had involved you squaring natural log. And you just need to know that this means this, and this is guaranteed that the bottom is positive. And I went through this pretty quickly because I've already talked about vertical asymptotes. So that's the vertical asymptote part. Is everybody kind of okay with the vertical asymptotes?
Yes, sir.
Okay.
Yes.
Yes.
Okay. Perfect. Y'all could could you turn your cameras on so I could see faces again? I know you get the habit of not doing it, but it was really nice Friday when I could see people. Thank you. All right. Yay, I appreciate it. Oh, enough people have conned on. I can actually do large gallery and see everybody. Oh, it's awesome. All right, so that is vertical. Those are vertical asymptotes. I do need to talk about horizontal asymptotes. And I like my version of horizontal asymptotes because the official version of horizontal asymptotes I'm not a huge fan of. Okay. So, horizontal asymptotes. Let's try to find a couple of them. So I'm going to start with what's the limit as x goes to infinity of 3x to 5x cubed minus 2x plus 4 over 3x cubed plus 4x minus 2. And I want to talk about, this is sort of limits at infinity. And this is a horizontal asymptote. Now, this is how I think of it. Whenever I'm looking for a horizontal asymptote, I am answering the question, what happens when x gets big? Right? And as silly as that sounds, that's exactly what this is saying. Right? It's actually what happens to y. This says what happens when x gets big. That's what limit means. Limit says what happens to y as x approaches something. In this case, that something is infinity. So what happens when x gets big? All right. The way I always present this is I talk about, let's say I'm graphing this function, and this is a pretty ugly function to graph. It's actually very ugly to graph. If you had to graph that last year without a calculator, it's miserable. Like this actually has the potential to have 3 vertical asymptotes. So if I were graphing it, I'd have the possibility of 3 vertical asymptotes. And at vertical asymptotes, the graph does all sorts of weird stuff. Sometimes it does this little S thing, sometimes it does this little parabola looking thing. But this question doesn't care about here. See, this limit as x goes to infinity, what happens when x gets big, is asking the question, what does my y value do way out here? See, when x is huge, see, this doesn't care about when x is small. This is like x is 2, x is 10, x is 20. This is asking what happens to my y value when x is huge, like x is 1,000,000. Meaning I'm plotting a dot way, way out here. And if you were in class, I could just start walking. I usually actually walk out the door, right? Because I'm trying to go as far to the right as I possibly can. All right? So, and that actually makes your life a lot easier because when you answer the question, what happens when x gets big, a lot of this function doesn't matter. See, let's look at this rational function. And we're going to deal with the top and the bottom separately. And I'm going to say, so when I say what happens when x gets big, I'm going to say, another way of saying it is what's important when x gets big. All right, let's look at this top through a certain lens. If you had $10 million and someone gave you $4, would you care about the $4? No, because you've got 10 million, right? So when x is huge, that 4 doesn't mean a whole lot. So we get to ignore it. And the same logic, you go through, well, if x is huge, let's say $10 million, can we agree that $10 million cubed is way bigger than just $10 million times 2? So when x is huge, these terms don't matter very much. In fact, when x is huge, the only thing that matters is that term with the highest power. So I'll go ahead and put the limit as x goes to infinity. So the only term that really matters is the term with the highest power, which is going to give me 5x cubed. The same logic goes on the bottom. When x is huge, what do you care about on the bottom? Well, that 2 doesn't matter because 10 million, you don't care if someone takes $2 if you've got 10 million. And then when you compare like 10 million cubed to just 10 million, this is way bigger. So when x is huge, these terms don't matter. So all that matters is this 3x cubed. Well, I can cross the x's out, and so we end up with 5/3. Now, here's what that means back to my picture. See, if I were to graph this in my calculator, I'd have some ugly graph. I have no idea exactly what it looks like. I just drew something random. But what does happen is, as I go further and further to the right, this graph gets really, really boring, right? See, right here, it's real exciting. Stuff going to infinity all over the place. But the further to the right I go, the bigger that x gets, my y values just get closer and closer to 5/3. And so I end up with the graph that just gets closer and closer to 5/3, and that's my horizontal asymptote. Same thing happens on the other side. If x gets really big negative, these terms don't matter. I'm just left with this. And so as I go all the way to the left, I don't know if it's coming from the top or the bottom, and I don't really care, but it's getting closer to this particular y value. So how I always teach horizontal asymptotes is I talk about what happens when x gets big, or what matters. Like, what's your most important term on top and most important term on the bottom? Now, there's 3 examples. Right? This is the first example. My next example is, what's the limit as x approaches infinity? What happens when x gets big? But now I'm going to have 5x squared minus 2x plus 4 over 3x cubed plus 4x minus 2. And so now I want to know, well, what happens to this as x gets big? Well, the good news is I asked the same question. What doesn't matter, right? What's important when x gets big? Well, when x is huge, these terms don't matter, so I'm just left with the limit as x approaches, limit as x gets big, of 5x squared over 3x cubed, right? Because when x gets big, these don't matter, because you only care about your highest power on top and your highest power on the bottom. this reduces, right? I can simplify this to say that's going to be the limit as x gets big of 5 over 3x. And now I look at this and I ask, what happens when x gets big? What happens to this value as x gets huge? So if I have 5 divided by a giant number, what happens? It gets smaller, doesn't it? Mathematically, we say that goes to 0. So what we just found out was, as x gets huge in this situation, because it's bigger on the bottom, right, then my y values get close to 0. So back to that picture I had, instead of everything getting close to a y value of 5/3, now everything gets close to a y value of 0. Now, last example. What if I have the limit as x approaches infinity of shoot. Now it is. Okay. All right. So, next problem. What if I do 5x cubed minus 2x plus 4 all over 3x squared plus 4x minus 2? And I still ask the question, what happens when x gets big? Well, when x gets big, this goes away and this goes away, so I'm left with the limit as x goes to infinity of 5x cubed over 3x squared. And let's see, this is going to reduce, that's going to give me 5x over 3. And now I ask, what happens to this as x gets big? Well, as this gets big, right, as x gets huge, this still gets big. So in this case, when x gets huge, this goes to positive infinity, and this means we don't have a horizontal asymptote. So, summary of horizontal asymptotes. I talk about balanced, and when I mean balanced, that means the exponents are the same. So if it's balanced, we get a number, right? We get something other than 0. I call this bottom heavy. And the reason I call it bottom heavy is, well, the exponent is bigger in the bottom, so this is bottom heavy. At any time it's bottom heavy, my horizontal asymptote is going to be 0. And this is top heavy, and anytime you have something that's top heavy, that means you don't have a horizontal asymptote. And we're going to talk a little more about that stuff tomorrow. Well, actually, no, we're not.